is described by its structure. Inside the network, each neuron's output is determined by the mathematical formula called activation function. The loss function. During training, the function evaluates how well the neural network did by comparing its output to what was expected. Reducing the loss function during training is accomplished by adjusting the weights and biases of the neural network using the optimal techniques. Regulation. This prevents the neural network from overfitting, which occurs when it belongs overly complex and starts to match the training data too closely, resulting in poor capacity to generalize to new data. By training, the neural network initial weights and biases are established by using initial procedure. The degree of modification of the weights and biases in each optimization algorithm iteration is determined by a parameter called learning rate. Next, after then the data was splitted. Using the sequence function, we built two LSTM layers, each consist of 50 neurons. After that, the model was trained over 50 epochs with the model fit generation function, and the outcome was shown. Here you can see redesign the neural network. The number of layers and the neurons in each layer of LSTM should be increased, in my opinion. Extending the time series input sequence to 70 times its length and reducing the test data ratio to 30% will help to further improve the prediction accuracy. And the report development, testing, and training of the model for estimating power consumption was the aim of the project. Our model was built using the long short-term memory recurrent neural network architecture in order to achieve this goal. With the help of Python Keras API, the model was built using two LSTM layers, each with 50 neurons, and dropout layer within. To compile the model, an Adam optimizer and a mean square error loss function was utilized. The fit generation the fit generator tool was then used to train the model for 50 epochs. The model's post-training performance was displayed using a line graph showing its low history. With the time series generator, creating a test set for both the model and the model, utilizing the predict generator function, generate predictions for the test set. Using the scale inverse transform method, we then restore normalized forecast to their actual value. The projections were then displayed against the actual value, and we compare the model prediction to the average of the actual value. When using the updated model instead of old one, we had somewhat better results. The expected value and the near value don't match. As seen in the image below, it followed the upgraded model yields some better result. By visualizing this image, you can see the blue line is total demand and the orange one is forecast. An overview of the revised core parameter. 30% of the data was used for testing. The number of LSTM layers in this are 3. Numerous neuron in every layer of LSTM is 50. Layer with dropouts, yes. If there is a dropout layer, the 20% reduction in proportion. A time series input sequence length is 70. Next comes the compare between network performance in this revised model specialization. It is extended sequence length of input 80, a large batch size of 35, enhanced number of training epochs is 100 assessment measures. Loss is the numerical indicates of forecast mistakes. Better fit is indicated by lower values. Predictions. The average of actual values was compared to the modified models expected values. Closer denotes more precious forecast. And the findings are loss. When compared to previous model, the updated model exhibited noticeably less low, less loss. The adjustment the adjusted model may now be better able to fit the pattern in the sequence data, as seen by the lower loss throughout the whole evaluation dataset. Reduced loss indicates better generalization. The predictions, generally speaking, updated predictions are far more accurate. High accuracy in prediction is suggested by improved performance on validation data that was not used for training, indicating that the updated model learned a more accurate representation of the pattern. The improved model capability when came from extended the batch size, number of training epochs, input sequence length, utilizing seem to have allowed to capture more dynamics in the sequence dataset. This was illustrated two ways. Firstly, better generalization, low value loss, and secondly, more skillful prediction on unseen data. Overall sequence modeling performance is improved by upgraded model over the baseline. Thank you.